D.Natelson will be presenting about noise measurements.
Hi, everybody. Thanks for sticking it out to the end. When I saw I was the absolute last speaker on the agenda, I got a little concerned, but hopefully you'll stick around because you want lunch. So I'm going to talk today about noise measurements in condensed matter physics. So this is kind of a boutique topic that I think is quite interesting, and I think, as I'll try and convince you, there's some real opportunities here in measuring noise, and I'm talking specifically about noise in transport. This is a bit outside the norm of what people typically do. We all know about doing electronic transport measurements and how fruitful this can be, but it is sort of a macroscopic average. It's a time average, and the question is, are there things we can learn by looking at things like not just the current, but say the fluctuations in the current, or not just the voltage drop across a material, but the fluctuations in that. So this is going to be, I'm trying to have this be pedagogical. I was warning Professor Jeb before that this is me cramming 2 talks worth of material into 1 talk. So if there's particular things, I've hidden some slides. If there's particular things you want me to spend more time on, please speak up. Okay. So what is noise, right? I mean, you kind of have this conceptual notion of what noise is. If you imagine here is the current as a function of time, and I've got some AC signal on my system, and this is kind of the ideal thing. And if I took a Fourier transform of this, I would find that it's got a whole lot of power spectral density, either in the voltage or in the current, right at the magic frequency where I'm driving the system, right? So we can talk about the frequency domain is a common way to think about noise, and we talk about power per unit bandwidth, or mean square fluctuations in the voltage per unit bandwidth, or mean square fluctuations in the current per unit bandwidth. Now, this might be a more realistic spectrum that you might get in the lab. If you're measuring something, we all know there's all kinds of fluctuations that may not be controlled by you, that go on top of your nice AC signal that you're using to try and drive your material. Now, if I Fourier transform this, I will still have a peak somewhere at the magic spot. I created this basically in I can't remember if I did MATLAB or Python, but I just added white noise on top of an AC signal to get that curve. So there are many different kinds of sources of noise in electronic measurements, and some of these are intrinsic. So that just means they're really truly unavoidable, and these are the noise sources that can contain important physics, right? There's also extrinsic noise. I mean, we can have, if I take a spectrum analyzer and I just hold out a coax out into this room, I will pick up noise signals from the monitors, noise signals from, I guess these are LED lights, not fluorescent lights, but you'll pick up the Wi-Fi network in the building. You'll pick up all kinds of stuff. Usually that's not very interesting, and you want to avoid it. So the motivation for doing noise measurements is what I've jokingly called the theorist fantasy, right? So imagine I've got some material, some system. Here I'm writing it as a resistor, and I apply a voltage, and I measure the current. And we all know if charge was a perfectly continuous quantity, then the current, which is the charge flow per unit time, that would be it. That would be the end of the story. The tricky bit is, the key idea of what I'm going to talk to you about is, at least one key idea, is that charge is granular, right? Charge is partitioned into discrete lumps, and ordinarily we think of these as having charge minus E. And in some sense, the theorist fantasy, if I want to know everything there is to know about how charge is transported through a material, what I really want to do is get the ordered list of the arrival time of every single electron that goes through my material. Because if I actually know the ordered list of the arrival time of every charge carrier, then I can compute everything. I can compute the average current, but I can compute all the higher moments of the distribution of the arrival times of the carriers. And maybe there's really important information hidden in there. So I will tell you, very, very occasionally, you can almost do this, right? That would be called full counting statistics. And there are occasionally times when you can pull it off in an experiment, but it's very challenging. So, what is charge noise, right? So charge noise are the current noise are the fluctuations as a function of time of the current away from its average value. And we usually express this in the frequency domain. So if you see S sub I, these are the power spectral density of the current fluctuations. It's going to have units of amps squared per hertz. We talk about noise power or power spectral density. Sometimes, and often what we actually measure in an experiment is not so much the current noise, but sometimes it's the voltage noise, right? So I take a voltmeter, some sort of voltmeter, and I put it across my device, and I look at the output of the voltmeter as a function of time, and I can compute the mean square voltage fluctuations, right? And again, I can do this as a function of frequency, and I can have this, volts squared per hertz, defining the voltage noise. And you can usually relate these two things to each other. If you know the differential impedance, if you know dI/dV or dV/dI, you can go back and forth between the current fluctuations and the voltage fluctuations. Sorry, Apple Podcasts is trying to interrupt my ability to do this talk. Hopefully you couldn't see any of that. All right. So how do we model noise in circuits? So conventionally, here's my real resistor, and how do we really model this? Well, usually we model this as ideal noise-free circuit elements with some sort of noise source. So if I want to measure model the voltage noise across this thing, I would imagine some sort of ideal voltage noise source that just gives you a fluctuating potential, and I would have an ideal resistor that is noise-free, and that's my equivalent circuit. Or I can think about current noise. I can think about some current noise source in parallel with my resistor, with my ideal noise-free resistor, and I can model it that way. So how you do the modeling can be very important with how you want to interpret the data. There can be a lot of subtleties here. Coming up with the right kind of equivalent circuit is very important. There's actually arguments back and forth among people sometimes about particular experiments, about whether people are doing this correctly. Okay, so let me tell you a little bit about the different mechanisms to generate noise and what these can teach us about the underlying physics. So the intrinsic noise sources, the ones I was telling you about that usually are actually physically interesting and are commonly used to really learn stuff. There's the Johnson-Nyquist noise, right? That's thermal noise. And we'll talk more about that in a minute, but those are equilibrium fluctuations in current and voltage, and they're really a consequence of thermodynamics and the fluctuation dissipation theorem. So if I just have some object and I could reach in with, completely non-perturbative, maybe purely capacitive potential sensors, like scanning single electron transistors of the sort of thing that Professor Jia does. If I can measure the voltage as a function of time across some small object, I would see that in thermal equilibrium, this thing fluctuates. All right. And it fluctuates in a way that's related to its impedance. So we'll talk about that in a second. One important aspect of this that I'll repeat later, Johnson-Nyquist noise does not care about the nature of your charge carriers. It doesn't really care about the nature of your system. It just cares about what the impedance of your sample is. Right. So I could have all kinds of different things but if in the end, if the complex impedance of the sample is the same, then the noise you'll measure will be the same. And this is a thermal equilibrium situation. A thing that I will talk a little bit more about towards the end, in particular, is something called shot noise, charge shot noise, right? What is that? That's the unavoidable, when I drive a system out of equilibrium, that is the unavoidable excess current fluctuations due to the fact that charge is granular. All right. The fact that there are basically statistical variations in the arrival time of the electrons, that gives us an additional fluctuation in the current. Now, what are extrinsic noise sources? Environmental pickup, I already alluded to, right? You want to make sure your experiments are shielded if you don't want to pick up, local radio stations on your experiment. And those are the least interesting sources of noise. There's something called flicker noise, which, again, I've got some slides on, which maybe I'll skip through depending on how slow I am in giving this talk. But what is flicker noise? Flicker noise, you've also heard of called probably 1/f noise. You may have heard of this. This is noise that really it corresponds to the resistance of your device actually varying in time. How can that happen? Well, there's a bunch of different possibilities depending on the microscopics of your system. I think we all like to think that if I've got a perfect ideal stoichiometric material that's just sitting there, then this shouldn't happen. But if I've got, even in semiconductors, if I've got defects, charge traps, things like that that can scatter carriers, and maybe their charge state fluctuates stochastically with time, that can actually make your resistance bop around. Okay. And so we'll talk about that a little bit later. One last one for this really a semiconductor particular thing is generation recombination noise, where if I've got a semiconductor, my number of charge carriers itself can just fluctuate as a function of time, as electrons and holes thermally are generated and then annihilate themselves. So there can be some actual fluctuations in the resistance due to just the thermal properties of the carriers coming and going. So let's talk a little bit about Johnson-Nyquist noise. So here's Johnson and Nyquist. By the way, I encourage you to read particularly Nyquist's original PhysRev-B paper. It's like 2 pages, 2.5 pages. It is one of the most clear presentations of this idea that you'll find. It's better than what's in most textbooks, honestly. So Johnson did the experiment, and Nyquist did the theory. And the idea here is if I've got a resistor, say, and I just look at the thermal fluctuations in the voltage across the resistor, because I've got, again, this was very much a kind of kinetic theory inspired idea. When Johnson was working on it, I've got some electron gas, and it's fluctuating all the time in thermal equilibrium. And sometimes there's more charge on one side, sometimes there's more charge on the other. And this just leads to potential fluctuations. But the fluctuation dissipation theorem limits how this works. So what you find is at sufficiently low frequencies, the voltage spectrum that you get across this thing is directly proportional to the temperature. It's directly proportional to the resistance, or the real part of the impedance of your system, and it's white. It's frequency independent. Now, it's not perfectly frequency independent. We'll talk more about that in a minute. You could flip it around, and instead of measuring the voltage fluctuations across my system, I could hook up an ideal ammeter, and I could measure the current fluctuations. And what I would find is that I get, again, something directly proportional to T, and G is the conductance. G is 1 over R. So it's inversely proportional to the resistance of the device. So you can do it. The usual derivation is based on imagining I've got like a 1D transmission line, and I terminate it with resistors. This was Nyquist's nice way of thinking about it. So in thermal equilibrium, we kind of know this is a one-dimensional cavity. And in thermal equilibrium, we know what the occupancy of the cavity modes is supposed to be. And you can ask, where did that energy come from and where is it going? It had to have been emitted by one of the resistors and is going to be absorbed by the other resistor. So that basically is the thing that tells you, in sort of a black body radiation kind of idea, that this noise spectrum is white until you get out to frequencies comparable to KT over H bar. Right. Then, as you might imagine, in some sense, in this picture, your cavity modes freeze out if KT gets small compared to H bar omega, where omega is some characteristic frequency. So just to give you, again, as an experimentalist, just to give you a sense of scale here, 20 gigahertz is 1 Kelvin, roughly speaking. Okay, 20 megahertz is a millikelvin, 20 gigahertz is a Kelvin. So that gives you some idea about how frequency independent and what are your frequency scales for looking at this stuff. Yeah, so again, here's a derivation of this, right? You've got a 1D transmission line. The modes are separated in frequency by c over 2L, where c is the speed of light and L is the length of this thing. You can talk about the number of modes per unit bandwidth. I don't know if people really benefit from seeing derivations like this. So in equilibrium, each mode of my cavity should have like basically a Bose factor occupation and should contain H times F, or H bar omega worth of energy. Sorry, my shirt is caught on the microphone. There we go. So you can basically work out the power being transmitted from one resistor to the other, and you can basically map this all out. And in the end, you can come up with the derivation that in fact the noise looks like the voltage noise, for example, looks like 4 times the resistance times basically H bar omega over e to the H bar omega KT minus 1. And if you basically take the high temperature limit, this basically works out to the formula I showed you before. So as I said, this kind of fluctuation does not care about the nature of your charge carriers. It's always there. It's unavoidable in equilibrium. And it's turned out to be very useful for thermometry. So there's lots of people who've done work on noise-based thermometers. Here's actually a really kind of a nice reference if you're interested, from a few years ago. And here is an example of data taken in my own lab. If I just take a resistor and we measure the noise across it and divide it by 4 kBr, where R is the measured resistance, and I plot that versus the temperature that I have measured with some other kind of thermometer, guess what? They really look like each other, right? I mean, this really does work over a very broad temperature range. One thing I will say is when you're out of equilibrium, it can be tricky to cleanly separate the non-equilibrium contributions to the noise and the Johnson-Nyquist noise, right? So it might be very tempting to say like, I'm driving my device is out of equilibrium, I'm at some bias, it's got some differential resistance, so I should just think that there should be Johnson-Nyquist noise that's given by 4 kT times the differential resistance, and that's how I should think about it. And the answer is you have to be very careful doing things like that. And you'll see kind of a more sophisticated way to think about this shortly. Yeah, so just something to bear in mind. But there's all kinds of very nice implementations of noise thermometry. On some level, this is a very reliable way. Whenever people tell you in dilution refrigerator experiments what the true electron temperature is, right? They'll say, oh, my mixing chamber is at 8.5 millikelvin, but my electrons are at 35 milliK. How do they know that? There's different ways to do it, activation energies of quantum Hall states, for example, things like that. But this is an extremely reliable way to do this stuff. By the way, please feel free to interrupt me if you have questions. So let's talk about shot noise. So this is Schottky, who has multiple things named after him. And so, a bit over 100 years ago, Schottky was worrying about the problem of noise in a vacuum tube, right? So if I've got a vacuum diode where I've got a filament and I've got some kind of that I'm going to have at a negative potential relative to some kind of anode that I'm going to have at a positive potential, I heat my filament up, I boil off electrons, I thermionically emit electrons, right? And what are the fluctuations in the current that go through this thing? And he treated this very much as a simple statistical process. So I'm driving a net current, so it's not in equilibrium. And I can just say, okay, let's model this as a Poisson process. This basically assumes the electrons don't talk to each other. It assumes there's some average arrival rate of electrons. This electron doesn't know when the last one came. It doesn't know when the next one is coming, but there's some average arrival rate of electrons. And you get current fluctuations because the charge is coming in discrete lumps. And there's just statistical variation in the arrival time of the electrons. Sometimes they come closer together in time. Sometimes they come farther apart in time. So you can actually do the statistics problem. And I've got a derivation on that. If people are interested, I can give you a reference for a nice derivation on that. But I'm not going to show you the full derivation. It's just some laborious algebra and a little bit of calculus to translate into the frequency domain. But the bottom line is, if I've got Poisson distributed charge carriers of charge minus E, then the mean square fluctuations in the current per unit bandwidth end up being twice the electronic charge times the average current. So in some sense, this is this is white. This is white out to some cutoff frequency. We can talk about the details of that, but it's not that different. The idea is not that different from what we were talking about with the Johnson-Nyquist noise. This is a consequence of the granularity of charge, and it is in principle, it's a way of measuring the charge of the electron. And there are a couple of multiple different universities that actually do this as an undergraduate lab. It's not that hard to set up something like this. And I know, in fact, a nice derivation of this is in the MIT has an online lab manual for their measuring the charge of an electron with shot noise lab that they do with a vacuum tube. And the write-up there is pretty clean if you're interested in the derivation of how you get to this. Okay, so shot noise itself is inherently current noise because it really comes from the statistical variation in the arrival of the charge carriers. Often we measure it in practice as voltage noise, right? You basically have some system and you put a voltmeter across it and you look at the fluctuations in the voltage and the resistance, so you can turn that into the fluctuations of the current. Now, we also often talk about something called the phono factor. Again, Ugi Phono, another person who has his name on many, many things. When you read a paper on this topic and someone talks about the phono factor of noise, what do they mean? They mean it's the ratio of the measured noise in an experiment to this Poisson factor. So a phonon factor of 1 means the system acts just like the vacuum diode that Schottky was worrying about. And that really does happen, particularly if I just have an ordinary tunnel junction, an ideal tunnel junction, right? Now, in an ideal tunnel junction, you can't measure this out to arbitrary frequencies because this thing has some kind of capacitance. So with any real setup, you'll have some RC capacitive roll-off at high frequencies, right? But if you look at low enough frequencies and you have your tunnel junction, or you put this thing as part of a measurement circuit, we'll talk about that in a little bit, you can actually measure the fluctuations in the tunneling current, and it really does work. You get a phonon factor of 1 in sort of ideal tunnel junctions. Okay, so how should you, boy, I really have no idea if this is going to translate, if you're going to be able to hear the sound when I click on this. Why do you care about this? Why is shot noise important? Well, the bottom line is that there's many different ways to get the same amount of current to flow per unit time, right? So think, if you will, about rain falling on the windshield of your car, okay? When you have some of the weather that we've had the last couple of days, if you have some weird rainstorm that's starting, the rain can come in a bunch of big droplets. We'll see if you can hear this. Totally not playing. That's disappointing. This is supposed to sound like a bunch of clicks, okay? Boy, that's really annoying that that's not playing at all. Okay, the point is that you can get a lot of a relatively small number of large raindrops hitting your windshield. Or, oh, now it's playing. Can you hear that at all? No. I'll turn my computer volume up. Okay. Or I can get the same amount of water, if you will, per unit time by having a large number of smaller blobs, right? So it's actually a little bit smoother in time. It's a little hard to tell. Or I can still get the same amount of water per unit time. So it's be like the same current if I have like a fine mist falling, right? So it actually is smoother to your ears, right? So basically, shot noise is measuring how charge is delivered. I should be careful. I should have revised this slide. It's not so much measuring the magnitude of the tunneling charge, but it's telling you whether the charges are coming more or less correlated in time, bunched or anti-bunched versus the Poisson result, right? If the phonon factor is less than 1, it means in some sense you can think of it, the charge is flowing more smoothly, right, in time, and there's different ways that can happen. We'll talk about that in 1 second. If the phonon factor is greater than 1, it kind of means charge is flowing in a way that's chunkier than just having the individual electrons going in a Poisson sort of way. So here's a diagram, and this will tell you a little bit about why it's hard to cleanly separate equilibrium and non-equilibrium noise. So what I've drawn here, this is the current noise as a function of current for and so down here, this is 4 kT over R, so that would be the Johnson-Nyquist noise. So thermal equilibrium is basically when I equals 0, so it's up against this edge, right? So I could have different kinds of systems, different kinds of devices, where they will all, if they all have the same resistance, if they all have the same real part of the impedance in equilibrium, then they will all give you the same Johnson-Nyquist noise. But as I crank up the bias and I drive this thing out of equilibrium, if the phonon factor is 0, I will just keep the Johnson-Nyquist noise. That's all that's going to happen. If I've got like a tunnel junction instead, where the phonon factor is about 1, you can imagine having Poisson distributed carriers going through, and that would give me my phonon factor of 1. My noise, this is called, sometimes shot noise is called excess noise, right? Because it seems to add on top of the Johnson-Nyquist noise. And then if the phonon factor is 2, imagine I've got Poisson distributed pairs for some reason. I've got some kind of superconducting device where under the right circumstances, I can see pairs coming. That would give me even greater noise, all right? Because the charge is coming in blobs, it's more bunched than the Poisson case. By the way, I should have said the other way to get no noise is to have the charge go through not so much as a perfectly smooth thing, but to have the charge go through in such a strongly correlated way that the electrons come through like clockwork, right? If the electrons come through perfectly evenly spaced in time, then there are no fluctuations in the current, so there's no noise. And an example of that can happen in the world of Coulomb blockade. You can make devices where Coulomb charging effects are very strong, and you can get electrons that are basically there's gatekeeping going on by interactions with other electrons. And so things go through one electron at a time like clockwork. All right. So I just want to show you that, if you assume the Fermi-Dirac distribution and the Fano factor is 1, this is actually what you get for what the current noise should be in like a tunnel junction. Okay. And this formula extrapolates in the low bias limit, it extrapolates to exactly the Johnson-Nyquist noise. And in the high bias limit, it extrapolates to the 2EI, right? The Schottky-Poisson result. And in between, it's more complicated. And the thing I want to point out about this is, if you look at this, okay, so if you look at this, what you can see is in order to actually get to this non-equilibrium limit where the noise is dominated by the shot noise, right, you have to be at large enough biases compared to KT. So one way to think about that is that if I don't drive my system hard enough, it's not really out of equilibrium, right? If my perturbation on the system is small compared to KT, then the system really is still effectively in equilibrium. So its properties are dominated by the equilibrium processes. Okay, so now if I actually have some Fano factor that isn't 1, right? What should happen? Well, the current noise should look like this. And this is very much an empirical thing. Imagine that there is a Fano factor that is independent of bias. What do things have to do? Well, if you look carefully at this expression, this still extrapolates to the Johnson-Nyquist noise at zero current, at zero average current, and it extrapolates to F times 2EI at high current. Okay. But this is why it's hard to necessarily cleanly separate equilibrium and non-equilibrium stuff in general. And of course, in real systems, the Fano factor, you could imagine circumstances where this Fano factor, which is tied to the way charge flows, it could depend on your bias. It could depend on the conditions you're applying. Right. Subtleties come up when devices are not ohmic. Do you want I over V here? Do you want di dV here? Right. What happens if d squared I dV squared is not zero? You actually need to think about that. Okay. So you might also ask what happens, and this is a situation that comes up. I'll tell you a story, a sad story. I had a student spend a lot of time unsuccessfully trying to measure noise in edge states of a 2D topological insulating system. And why was this a problem? The problem was that the contacts, like what you want to do is you want to measure you think to yourself, I've got this exotic 2D topological insulator. I'm supposed to have chiral edge states. I should really be able to see whether they're, the quantization of current in these edge states doesn't seem to be perfect. Why is that? Maybe I can learn something about the scattering mechanism. The tricky bit, and this comes up in some of these 2D systems, is I have to make contacts to these things. So the real thing I'm measuring, right, is I've got my, and it can be very hard to do like a 4-terminal type measurement. So I can have a situation where like essentially I've got contact, my device, another contact, right? And I'm really somehow measuring the sum of this. So how should you think about tunnel junctions in series? You can model this, Landauer, very far-thinking IBM theoretical physicist, was worrying about this in the 90s. And basically, if I've got a bunch of tunnel junctions in series, what happens is that the shot noise gets divided by 1 over the number of tunnel junctions. So it can be a real problem if I've got a device and my contacts are not somehow noiseless, and have noise that depends on the bias. Like if all they do is contribute Johnson-Nyquist noise, you're okay. But if they're actually really kind of tunnel junctions and they contribute their own noise, you can run into real challenges this way. Okay. By the way, at the same time, the Johnson-Nyquist voltage noise is enhanced if I have a whole bunch of things in series, right? Because my resistance is getting bigger, so my voltage noise is getting larger. Okay, so one other thing I want to talk about, I'm really kind of I know this is a little far away from the world of strong correlations, but it's related, and you'll see why in a minute. So there's this thing called the Landauer-Bodecker approach to transport, to mesoscopic transport. If I've got small systems, right? What you can do is, yeah, so in the semi-classical world, we can usually ignore quantum interference. There's, quantum coherence corrections to classical conduction, right? But the Landauer-Bodecker approach basically says, I've got my little device, and my conduction process is really transmission of some kind. I can send in carriers, and they're either transmitted or reflected. And by the way, if you want a good reference on this, this is a pretty nice book by Supriyo Datta from Purdue. So the idea here is the conductance through some small region, right, is given by 2e squared over h, if we're assuming that there's no spin physics going on, times the sum of the transmittances of my different quantum channels that get through my little region. So some channels are maybe this channel is transmitted perfectly, this one's partially reflected, this one's reflected a bit more, so its transmitted amount is less, right? So the conductance has to do with the sum of all these transmittances. So you can actually do, again, a really nice, very encyclopedic review by Blanter and Bodecker from a while ago, really talks about all of this. You can worry about what the noise is in something like that. And because there's some probability of things getting transmitted and some probability of things getting reflected, what you find is that the noise has the transmittances hidden in it. So the phono factor for some little mesoscopic thing involves the sum of transmittance times 1 minus transmittance over the sum of the transmittance. What does this tell you? It tells you that if I've got perfectly transmitting pathways through my little system, that they don't contribute to the noise, because the phono factor goes to 0 if for a particular channel, if the transmittance of that channel is 1. So if I have ballistic conduction, then my shot noise should go away. Okay, so generally phono factors are less than 1. If you look at these formulas, if I have a single weakly transmitting channel, which is basically typically what happens if I have like an STM tip and I'm going to have it near a surface, usually this is the reason STM is amazing. Its conduction is dominated by that closest atom, right? So the phono factor approaches 1. So if I've got finite temperature, I need to actually take into account the Fermi-Dirac distribution. I get something more complicated looking. And like I said, it is not trivial to separate the thermal noise from the shot noise in a system like this. Now, why am I telling you this mesoscopic thing, which kind of ignores electron-electron interactions? Why am I telling you this story? Okay. I want to show you a couple of things. So like I said, a fully ballistic channel does not contribute to the noise. And this is one of the earlier noise experiments, right? This is this beautiful work by basically Moti Heibloom's group at the Weizmann Institute back in the 30 years ago now, where they made a quantum point contact, right? Took a 2D electron gas, put some gates on top of it, applied negative voltages to those gates to pinch off the conduction through this point contact. And what you see is that the conductance through the point contact drops in integer multiples of 2e squared over h. This is conductance quantization. It's one of these beautiful things, right? Pinching off the contact, pinching off the contact, pinching off the contact. And they measured shot noise simultaneously with this. And what they see is basically the noise is suppressed when you're on one of these conductance plateaus. If you're getting good transmission, ballistic transmission through your little quantum point contact, your noise is suppressed. And in fact, in my own group, again, boy, it's hard for me to believe this was 13 years ago now. We did some experiments. You can get this kind of conductance quantization stuff even at room temperature if you make the devices small enough. So if I basically take a gold atomic scale point contact and I make and break it, you will see that the conductance tends to have, if I histogram that, the conductance tends to have a big peak at 1 G0, which is basically when you've got a single atom making the contact between the two sides. And you can simultaneously measure the noise while you're doing this. These contacts don't last very long, so you have to do kind of a high frequency way of measuring the noise. And what you see is, yeah, lo and behold, the noise is in fact suppressed right when the conductance is what you'd expect for a quantized, perfectly transmitting channel, right? Why isn't the suppression perfect? Well, the answer is sometimes you can get a conductance of 1 by having 2 partially transmitting channels, right? If the only way to get a conductance of 1 unit was to have a single perfectly transmitting channel, you would expect this to go all the way down here to 0. Happy to talk about that more. So the other reason I'm telling you this is because it connects to an example I'm going to give you of actual measurements we've done on correlated things. Okay. So you might ask, what happens if if I don't have like some very tiny mesoscopic thing, right? What happens if I've got like a wire? That seems a bit more interesting, right? More feasible to do with some of these more exotic materials. What if I have a wire with many transmitting channels plus some amount of disorder? I'm going to assume my electrons are diffusing through the wire because they're scattering off of disorder. So you can treat this problem in 2 different ways and get the same answer, which is always nice. One approach is you can take what I just showed you, right? And if I do basically random matrix theory, and I do some kind of average over, if I say I've got a lot of channels and I don't know much about the transmittance of each channel, but I can do some sort of ensemble average over the possibilities, what you find is that this complicated expression for the phono factor goes to 1/3. Kind of nice. So if I have an elastically diffusive constriction, I just have a wire where I'm ignoring electron-electron interactions, I'm ignoring electron-phonon scattering, I should get a phono factor of 1/3. There's another way to derive this, which probably is more useful if you want to think hard about what would happen in strongly correlated materials. Yeah, here's the reference for that. You can get the same result if you think about the distribution function for the electrons everywhere, okay? So imagine I've got a Fermi liquid, I've got a source, I've got a drain. My electronic distribution in the drain is shifted relative to that in the source. This is supposed to be a Fermi function, a Fermi-Dirac function. They're shifted relative to each other by EV because that's the bias I'm applying. So if I don't have any electron-electron scattering, the distribution function in the middle of the wire actually looks like this. It's got 2 steps. Some of the carriers that are coming from one side have the chemical potential of one side. Some of the carriers coming from the other side have the chemical potential of the other side. So in the middle of this wire, if I don't let the electrons talk to each other, and I don't let them talk to the rest of the world, they have a very peculiar distribution as a function of energy. And it turns out you can go into kind of a Boltzmann formalism and turn the crank. And if you actually ask, what are the current fluctuations if I locally, as a function of position in the wire, worry about the non-thermal distribution function of the electrons in the wire, you get the same 1/3 answer. Okay. So again, this assumes no electron-electron inelastic processes. It is, and basically it ignores the existence of phonons entirely. And Nageyev did a really nice job on this. Okay, so let me give you an experimental example. This is measurements we did in our own lab. Here's a gold wire, right? It's, kind of short, maybe 700 nanometers long, a little less. It's pretty skinny. It's kind of 100 nanometers wide, 70 to 100 nanometers wide. And what we have here is I've plotted it as voltage noise versus the bias current, okay? But what you find is that this upper dashed line is what you expect if the phono factor is 1/3. You can see you kind of get some curvature up in there because that's basically EV exceeding KT, right? And what you see is that the phono factor really is about 1/3, right? Here, 3K, 5K, 7K, 10K. So this actually does work. And now if you keep going up in temperature, what happens? Well, eventually phonons matter. We're going to talk more about that in a second. But what you find is that the phono factor starts dropping, and we'll return to this shortly. So what about electron-electron scattering, right? What happens if this seems like it might be really important for correlated materials. What if the electrons scatter off of each other? What does that do to the noise? And by scatter off each other in this context, I mean they exchange energy. So in the Landauer-Bodecker picture, electrons scattering into each other, you can scatter from one channel into another, but you really don't remove any energy from the electrons, right? In the distribution function language, if you really turn up electron-electron scattering, what happens is the electrons locally achieve some kind of Fermi-Dirac distribution with some local temperature that's elevated from what the equilibrium situation is. So if you can worry about what that is if you just ad hoc assume that the electrons have achieved some local temperature. You can do a little toy model and say, well, if E here is the electric field, I can basically say Joule heating, energy from the Joule heating has to be transported out by thermal conduction out of my wire. You're basically hidden in here is the Wiedemann-Franz law. And this will tell you what the temperature is a function, the effective temperature as a function of position is in your wire. And you can basically work out what this does to the noise. And you end up with something where the noise still is proportional to the current. So it looks like shot noise, but the effective phono factor is actually bigger. The effective phono factor is not a third, which is what happened when the electrons can't exchange energy, but the effective phono factor becomes √3/4. Okay, this is actually pretty hard to see in experiments, by the way. Some of the people who have seen it in experiments, or at least reported it, were people like Michel Devereux and John Martinez, whose names may be familiar to you if you're into quantum information. These are serious people. But the point is that instead of your distribution function having this funny two-step situation, it's just got some smeared out higher effective temperature, and that gives you the √3/4 for the phono factor for noise in the limit where just the electrons carry the charge, but they talk to each other. What about phonons? So it really kind of, how phonons figure into this depends on the kind of system you're thinking about. In general, if I have an extended system like a wire, electron-phonon scattering suppresses the noise. Now, why would this be? Well, if you think about a limiting case, imagine that the electrons talk to the phonons all the time, right? That just means that the electronic distribution function is always going to look like a Fermi-Dirac function at whatever the phonon temperature is. If that's true, then even when I apply a bias, if they talk to the phonons rapidly enough, it doesn't matter. I never really perturb my distribution function. It's always going to look like a thermal distribution function at the lattice temperature. And so I'm only ever going to see Johnson-Nyquist noise at the lattice temperature. You can do a better treatment of this, right? You can do something a little more sophisticated. And again, people were doing this in ordinary conventional metals, weakly correlated metals back in 25, 30 years ago. So again, here's my situation where I'm going to imagine my energy is locally appearing in the electrons due to Joule heating. It can be conducted out of the ends of the wire, or locally it can escape to the phonons, right? I can parameterize the energy loss of the electrons from the electron system to the phonon system by some number that we'll call capital gamma, because that's what other people called it. So you can go and you can solve, you can see what happens. Usually the thing to do is to assume that my contacts at the ends of my wire are big and thick and very well heat sunk. Ordinarily, if I've got kind of an ordinary Fermi liquid, I assume I'm in the limit of kind of residual resistivity if I'm at low temperatures and trying to do this. And so depending on the magnitude of gamma, my temperature profile can get very, very flat. If I make gamma really large so that heat energy loss to the phonons is very rapid, my local electron temperature never gets very big. And it's basically constant in the middle of the wire because all the energy is going into the phonons, not getting conducted out the ends. Bottom line, you can actually basically do noise measurements in long wires and infer gamma for your system, okay? So for gold, this has been done by these folks and a couple of other groups, and we did it ourselves. Gamma, a decent number for gamma in this equation here for gold is about 5 × 10⁹ in SI units. I didn't have any intuition for this, but I'm just giving it to you, just to give you a sense of this. Now, what happens, what this means is there's some effective length scale, some electron phonon length scale where you really start dumping energy into the phonons. What happens if I take a gold wire and I make it longer and I keep increasing the temperature? So what you find, here's some more recent data from our group. Here's a almost 3 micron long gold wire, and you keep cranking up the temperature, and what you find is that, yeah, the phono factor, the noise just gets smaller and smaller and smaller. So eventually you really do kill the noise with phonons, right? There's a reason why it's hard to measure to do these experiments in bulk materials at room temperature. There's a reason why you don't see shot noise coming out of your wall plug, right? At 300 Kelvin, interactions with phonons are very strong. Okay, so here's the whole picture for a diffusive wire, right? If my wires are so short that things are basically ballistic, I get suppressed noise. If I'm in the limit where the electrons don't have time to scatter off each other, I get a phono factor of 1/3. If I'm in the limit where the electrons talk to each other a lot and can exchange energy, but they can't talk to the lattice yet, I'm supposed to get √3/4. And if I make a long wire, my noise gets suppressed again. Okay. All right. So how do you actually do the measurements? I just want to say a few words about experimental techniques, and then I'll show you a couple of examples, and I'll finish up. I don't want to keep you too late. I guess I have until 11:20 or 12:20 rather. Okay. Okay. So at low frequencies, here's the method that we've been using in our lab because it's got certain virtues of being extremely simple. All right. What you do is you just take your device. You have some circuitry for biasing it. You try and have some filters on there to make sure you're not like dumping noise from your batteries or your power supply onto your device. And what you do is you just take some voltage amplifiers and you measure the voltage across your device. But what you're going to do is you're going to do something somewhat clever. Your actual amplifiers in real life have their own amplifier noise, right? What you do is you take 2 amplifier chains and put them in parallel across your device, because you like to think that if there's a real fluctuation on your device, it gets picked up by both amplifier chains. But if there's something goofy happening at the input stage of one of your amplifiers, it won't be happening in the other one. And if I basically correlate these things, I can get rid of that, right? So you try and correlate between the 2 amplifiers. It works pretty well. The best thing you could do would actually be to have your first stage amplifiers be very cold so that their intrinsic noise is very small. And ideally you want the wires to be really short. So this capacitive roll-off problem that I mentioned earlier isn't there, or is very much minimized. That would be the ideal situation. Right. So what's nice about this is you can directly just measure the Johnson-Nyquist noise, right? You can just do it. And that tells you as a way of calibrating to make sure your gains of your amplifiers are well known and everything works, right? And if you're at low frequencies, you don't really have to worry about impedance matching or anything weird, anything complicated. So another approach is you can so what I just described is a very broadband thing. I'm going to Fourier transform stuff and get a full noise spectrum. That has some disadvantages. You can pick up random peaks from the lights and things like that. Another approach is you can make basically a tank circuit, a so-called tank circuit, an LCR resonator. And that is clearly going to have a, some peak in its response function, right? And you can, you're basically making a narrow band measurement instead of a broadband measurement. You need to calibrate it, right? So it's a little annoying to calibrate. But it has certain advantages that, if you know there's extrinsic noise sources that you're trying to avoid, you can work in just a bandwidth where you only think you're going to see the stuff you care about. At higher frequencies, you can do some broadband ideas about just integrating the total noise power. So this is actually what Heibloom did, and it's the approach that we basically borrowed when we did our measurements on those little atomic scale gold junctions. And you basically just do some sort of high frequency measurement, and you can use what's called you can just have a power detector, and you can just integrate all the high frequency stuff coming off your device over some big bandwidth, and you can modulate the current, and you can say, gee, if I'm driving a DC current, my high frequency noise should be produced by having charge flow. and you can do those kinds of measurements, right? This is basically the version that we had. You know, we turned our current on and off as kind of a square wave. We sat here with a power detector and measured the change in the noise across our little mechanical break junction. You do need to calibrate it, right? And these high frequency techniques start becoming tough if the impedance of your device is very far from 50 ohms. All your nice radio frequency electronics that you can buy assumes, you know, the world is simple if the impedance is 50 ohms. One of the real challenges with some 2D systems, you know, there's a few things, right? One is that these things are often can be very non-ohmic. But the other thing, and their impedance can be very complicated. But the other thing is they can also typically have a resistance on the order of h over e squared, or have it be like 13 kilo ohms or 26 kilo ohms or something. So you have to be careful about impedance matching if you want to do this stuff. Right. You can, again, do tank circuits. You can watch RF power turn off and on. Here's, you know, again, another example of this. You can make little resonators. If you have a non-ohmic device, like if you basically make a tuning circuit, but then your device is under different bias conditions, if it's conductance and if its impedance changes a lot, this technique kind of is almost unusable. Let me return to something I mentioned at the very beginning of the talk. It is actually possible to do full counting statistics under the right circumstances. Here's a really cute experiment, actually done by someone who used to be at Rice, where here's a quantum dot, and we're going to have charge tunneling on and off this quantum dot. And nearby, we're going to use a single electron transistor to detect when that dot has charge on it. And if the current is flowing slow enough, you can actually watch, you can basically get a click every time an electron goes through, right? So you really can do time-resolved measurements. But it's really, really hard. Like it works best at very, very low currents. If you think about it, if I have like basically less than a nanoamp of current, that's electrons going through faster than 5 gigahertz. Okay, so you know, the bandwidth is tough. Let me just say a few words about flicker noise, and then I'll skip a couple of slides to get to the in the last few minutes. So I told you that you got this problem where in some materials, the device itself, the material itself can have fluctuating resistances. This is really annoying. And the reason it's really annoying is if the resistance fluctuates and you look at the voltage noise power, basically I times the fluctuation in the resistance. If you square that, that gives you the fluctuation in the mean square fluctuation in the voltage. So basically you have a thing that goes like I squared, that it has nothing to do with interesting physics necessarily, right? So you really do have to, you know, there's some nice review articles about this, but it can be very annoying in some materials. And I'm happy to answer questions about that. Okay, why don't I skip a few slides about this? Okay, let me give you 2 examples about actually noise measurements telling you something about correlated systems. There's a number of these out in the literature, but I'll do a very famous one, and then I'll do something we did, and then I'll be done. Okay. The famous one, which was cited in the Nobel citation for the fractional quantum Hall effect, was there were 2 measurements that were done, one by this group at Saclay in France, and another by the Israelis, by Heibloom's folks in Israel, measuring the current noise in edge states in the fractional quantum Hall regime, right? They made some kind of interferometer, and they actually looked at, in the nu equals 1/3 fractional quantum Hall regime, they looked at backscattering when you bring 2 edge states very close to each other. And the idea here is to somehow get a sense of what what's going on with the quasi-particles of the fractional quantum Hall liquid, right? And so, you know, here's their experiment. This is what they expected to see if the charge, if in fact the quantum Hall state has charge E over 3. And they did this cross correlation method, the French guys did. And guess what? They really did see that the noise looks like, you know, here's noise versus backscattering current, and they see a phono factor of 1/3. And they know they're not really in this diffusive limit. They know they're looking at edge states because it's the quantum Hall effect, right? And so they got this very pretty result. And it basically at the same time, the Israeli group did this. They did a higher frequency approach. Here's them checking that Johnson noise works, and they too saw E/3 for filling factor 1/3. And this is evidence. This is noise as a way of giving you evidence that the fractional quantum Hall effect, the fractional quantum Hall liquid has fractionally charged quasiparticles. Now this is very subtle. And in fact, relatively recently, the same group has published a Nature Physics article saying shot noise does not always provide the quasiparticle charge. Okay, particularly in quantum Hall systems, fractional churn insulators, you can have neutral modes that can mess with you. So it's very subtle, and I honestly don't know enough to get into it. All right, last 5 minutes. Let me tell you about a relatively recent result from our group. So ytterbium rhodium 2 silicon 2 is an example of a strange metal. Okay, this is a quantum critical heavy fermion system where it is clear that something very funky is going on in the quantum critical regime, and it's basically at the cusp between a quantum phase transition between having one kind of Fermi surface and having another kind of Fermi surface. All right. And so and it's got this strange metal behavior. I should have included a couple of slides on that, by which I mean it doesn't look like a Fermi liquid. Okay, it looks like the resistance at low temperatures, the resistivity goes linearly with T, not quadratically with T at low temperatures. So strange metals are observed in a number of systems, and the question is, what's going on here? How should you think about quasiparticles in the system? And over the time period of a number of years, in talking with Professor C, but in talking with Silke Pashin, whose group grew these wonderful films, we thought for a long time about doing this experiment, right? I should point out, if you want to do experiments on some of these materials, you actually do have to make them into nanostructures, which can be tough, right? So Professor Pashin's group can grow these beautiful epitaxial films. My student figured out a way to pattern these things into wires without ruining them. One of the big challenges is doing measurements, before and after you pattern them to convince yourself you have not totally ruined the interesting properties of the material. That is a real problem with some systems. I just want to show you that in both the wire and the unpatterned film, the resistance is linear in temperature at low temperatures. The magnetoresistance is the same before and after you pattern it. Here's the wire. Here's the big, thick gold pads. And the bottom line is, when we did these measurements, the phono factor does not seem to be 1/3. The phono factor also does not seem to be √3/4. The phono factor seems to be quite strongly suppressed in this system, in this quantum critical regime, right? Now, you could worry that this is phonons. I apologize for going so fast. I just don't want to run too late. You could worry if this is phonons. But the bottom line is we did that experiment I mentioned with long wires where you can try and quantify how important is scattering to the phonons. And the answer is it's maybe a factor of 2 stronger than in gold, but actually that doesn't mean very much. To explain the squished noise that we saw, you would actually have to have suppression on the order of a factor of 70 bigger than gold, right? So yeah, we don't think it's due to phonons. You can worry about whether non-ohmic corrections matter. There's different ways of modeling this. The answer is no, it doesn't matter. The noise is just robustly small. What phono factor you pull out depends a little bit on how you fit it. But the bottom line is the phono factors really do seem to be small. You could worry if this is a finite temperature Fermi liquid effect, and Professor C's group has done some very nice work on this. The answer is basically no. That doesn't seem to explain things nicely either. Just again, here's the comparison. Here's gold as a function of temperature, and here's this unusual material as a function of temperature, right? And the conclusion we drew in the paper is that the greatly suppressed noise seems to imply that quasiparticles are just not well defined in this system. Remember, you can imagine if charge was a perfect fluid and there was no discretization of charge, I would get no noise. So so one thing I'm happy about is that this work has prompted a lot of effort. right? There's a number of theory papers that have been looking at this. I probably need to update this slide. But the bottom line is, it's an exciting time, right? So this is my second to last slide. I just want to say I'm a bit of an evangelist. Back in the 90s and the early 2000s, there was a lot of work done on these kind of mesoscopic scale measurements in nanostructures, looking at various things. And I feel like the community as a whole kind of considers that work to be complete and done, and there's a bow tied around it. But I'm trying to evangelize the idea that some of those measurement techniques that, yeah, people maybe did this to death on quantum dots in 1999, but if we apply them to some of these strongly correlated materials, they may have new things to teach us. So I'll just put up a summary here. I think I've convinced you that, what noise is. Johnson-Nyquist noise is this equilibrium thing. Shot noise is, in some sense, the intrinsic non-equilibrium fluctuations that result when you drive something out of equilibrium, and really has to do with the discretization of charge. Flicker noise is this annoyance that really has to do with basically defects, usually in a material, and you'd love to eliminate that because it gets in the way of trying to measure these more interesting kinds of noise. Though occasionally flicker noise can actually tell you physics too. There's a bunch of different ways to try and measure noise. They all have their trade-offs. And I hope I've at least convinced you that noise measurements in correlated systems can be rather revealing. You can get unexpected results. And I think there really are a lot of opportunities here for both theory and experiment. There has not been a lot of theory work done on thinking about noise in systems. There are some exceptions. I mean, there are people who have thought hard about what the noise would be like in Kondo systems, in Kondo quantum dots, in wires with Majoranas at both ends, things like that. But I still think it's kind of underexplored, partly because it's so challenging to do the calculations. All right, with that, thank you very much for your time. Okay, so clearly we would very much like to, there's a couple of things we would very much like to do. One thing is have films where we're able to measure them at lower, in this particular material, you need to go to lower temperatures, which in principle can be done, and silica can do that. One of the challenges is getting the film quality to remain really high while we do the fabrication to have, but yes, we'd love to do that. What you'd like to do is to have a knob like magnetic field and tune in and out of the non-Fermi liquid regime, right? Or the coherence becomes much worse and the quasi-particles are not well defined, right? But I mean, yeah, and again, it's something I'm very interested in, and I've talked with Yang and others about, it would be great to look at some of these other systems where people claim there's strange metal behavior and look at those as well, right? Because the question is what we're seeing particular to this kind of quantum criticality, or is it a more universal feature of these, these strange metal style non-Fermi liquids? We could talk about that more. So you mean in this particular material, or right? So it's not. By the way, you don't necessarily see exotic non-Fermi liquid behavior in all systems with phase transitions, right? With magnetic ordering, or even quantum phase transitions don't always seem to give you this phenomenology. You would probably know better than I, because I know you've looked at a lot of this. It's not always T-linear, and yeah, and I mean you could I mean I think it's kind of an open question, right? I mean in general, if I just look at magnetic ordering, and I'm not dealing with something with quantum, if it's not a second order, if I don't have quantum critical fluctuations, I don't think anything. I think everything that you would see in the noise would go along with what you see in the resistivity, right? So, there are systems where, when the spin disorder scattering turns off, the resistance drops, right? And I think you'd see that as a change in the Johnson noise, but I don't think you'd necessarily see anything exotic happening.
All right, let's close the session. I think we have a quick
Okay.
I guess we can move all our other questions to the lunch.
Sure.
So I guess that concludes the